Troy, New York, 1865. The metallurgical report from visiting British steel experts would never fully capture what they witnessed that autumn morning. American engineers, producing steel using methods that violated everything European tradition said was necessary for quality metallurgy. Through the roar and sparks of the New York foundry, molten iron transformed into finished steel with timing that seemed impossible to Sheffield observers. No 3-hour crucible firing, no careful temperature monitoring, no gradual chemical refinement. Yet they created steel with consistency that European methods required half a day to achieve. In British foundries, master steelmakers needed over 3 hours of precise crucible work to produce a single batch of quality steel. Each heat was carefully controlled, monitored temperatures, gradual chemical changes, extended refining processes. Most carried costs only premium manufacturers could afford. The Americans were operating with industrial philosophy the Europeans had declared suicidal. 20-minute conversion cycles, violent oxidation reactions, high-temperature chemical transformation that happened faster than human control seemed possible. 3,000 miles from Sheffield workshops, the most decisive metallurgical revolution in industrial history was revealing itself. Not through superior materials, not through centuries of tradition, but through systematic engineering that solved problems, in ways European steelmaking never imagined possible. The delegation from Sheffield arrived at Alexander Hawley's Troy plant on a crisp October morning in 1865, their leather portfolios thick with metallurgical reports that would soon become worthless. Leading the group was Edmund Richardson, whose family had operated crucible furnaces for 3 generations, producing steel that graced the finest British cutlery and the most prestigious engineering projects across the empire. Richardson carried himself with the quiet authority of a man whose methods had never failed, whose steel had never disappointed, and whose understanding of metallurgy was built on centuries of proven tradition. Hawley met them at the plant gates, his shirt sleeves already rolled up despite the early hour. At 33, he possessed the restless energy of an engineer who saw problems as puzzles waiting to be solved rather than barriers to be respected. The $100,000 he had borrowed to purchase Henry Bessemer's American patents represented more money than most men saw in a lifetime, enough to bankrupt 3 generations of his Connecticut family if his gamble failed. Yet as he guided the British experts through his facility, his confidence seemed unshakable. "Gentlemen," Hawley began, his voice carrying over the industrial din, "what you're about to witness challenges every assumption about steel-making timing that has governed our industry for centuries." Richardson exchanged glances with his colleagues. They had reviewed Bessemer's Sheffield demonstrations extensively. The process appeared sound in principle, forcing compressed air through molten iron to burn out impurities, but the speed concerned them deeply. Quality steel required time for chemical reactions to stabilize, for temperatures to equalize, for impurities to separate properly. 20 minutes seemed impossibly fast for metallurgical precision. The massive converter dominated the center of the plant floor like a mechanical dragon. 15 feet tall and pear-shaped, it was mounted on pivoting supports that allowed it to tilt for loading and pouring. The sight was simultaneously impressive and unsettling to men accustomed to the controlled environment of crucible furnaces, where steel developed gradually in small batches under careful supervision. "Your crucible methods in Sheffield," Hawley continued, addressing Richardson directly, "require 3 hours minimum per heat, correct? And you produce approximately 2,000 tons annually across your entire district." Richardson nodded curtly. "Quality cannot be rushed, Mr. Hawley. Our steel has built the finest ships and bridges in the world. When lives depend on metallurgical integrity, patience becomes a virtue." "Patience," Hawley repeated, almost to himself. "Let me show you something different." The demonstration began with 25 tons of molten iron, heated to precisely 1,600 degrees Celsius in the adjacent blast furnace. As the glowing metal flowed into the converter through carefully designed channels, Hawley explained his modifications to Bessemer's original design. The Americans had reinforced the converter shell with additional steel bands, redesigned the air injection system for more precise pressure control, and develop new refractory brick compositions that could withstand the violent chemical reactions. At precisely 11:42, Hawley signaled his crew to begin the blow. Compressed air roared through the molten iron at tremendous pressure, creating a spectacle that defied every principle of controlled metallurgy the British experts understood. Flames erupted from the converter mouth like a volcanic explosion, climbing 30 feet into the air with temperatures that made the observers step back instinctively. The sound was deafening, a continuous roar that seemed to shake the entire building. "The carbon is burning out," Hawley shouted over the noise, pointing to the flame colors. "Watch how it changes from yellow to orange to blue. Each color tells us exactly what's happening inside chemically." Richardson watched in fascination and horror. The violence of the reaction seemed antithetical to everything he understood about quality steelmaking. In Sheffield, crucible masters monitored their furnaces with quiet precision, making subtle adjustments based on decades of experience and careful observation. This American process appeared to depend on controlled chaos, trusting chemical principles to work faster than human judgment could follow. 18 minutes after the blow began, the flames suddenly dropped and changed color. Hawley's master blower, Thomas O'Brien, made a subtle hand signal. The air was shut off, and the converter tilted to pour the steel into waiting molds. The British delegation examined the finished product with instruments they had brought from Sheffield. The carbon content measured precisely 0.4%, perfect for railroad specifications. The steel's grain structure, revealed under microscopic analysis, showed uniform composition throughout. By every technical measure they could apply, the American steel matched or exceeded the quality of their best crucible products. Richardson found himself struggling with cognitive dissonance that would haunt him for months afterward. "Mr. Hawley," he said finally, "your results appear sound. But surely this level of production cannot be sustained. The equipment stress alone—" As if summoned by his skepticism, a problem revealed itself immediately. The converter bottom, subjected to 20 minutes of chemical violence at extreme temperatures, began showing signs of severe wear. The refractory bricks, designed to withstand normal furnace conditions, were crumbling under the combined assault of heat, oxidation, and molten metal flow. "There," Richardson said, pointing to the damaged lining. "Quality steel requires equipment that lasts. Your converter will need complete rebuilding after every few heats. The downtime will eliminate any speed advantage." Hawley examined the damage with the calm expression of an engineer who had expected this exact problem. "You're absolutely correct about the equipment stress," he admitted. "Traditional repair methods would require 24 hours of cooling, reconstruction, and reheating. That would make the entire process economically impossible." The British experts exchanged satisfied glances. American impatience had indeed met metallurgical reality exactly as they had predicted. Richardson began composing his report mentally, explaining why Bessemer's process, while technically interesting, could never compete with proven Sheffield methods in practical application. But Hawley wasn't finished. "Gentlemen, you've identified the central engineering challenge perfectly. The question isn't whether this problem exists, it obviously does. The question is whether American engineering can solve it in ways that European tradition hasn't considered." He led them to his workshop, where detailed drawings covered every available surface. The plans showed converter modifications that seemed to treat the bottom wear problem not as a limitation to be endured, but as a design opportunity to be exploited. Instead of building converter bottoms to last indefinitely, Hawley proposed making them deliberately replaceable. "What if," he asked, "instead of seeing equipment failure as the enemy of speed, we designed our systems to fail quickly and recover even faster?" The concept was so contrary to established engineering wisdom that Richardson struggled to process it intellectually. European steelmaking was built on the principle of permanent, robust equipment that operated reliably for decades. The idea of designing machinery to break down seemed like engineering heresy. As the British delegation departed that afternoon, their observations would fill reports that questioned not just American methods, but American engineering philosophy itself. They had witnessed steel production that achieved impossible speed with apparent quality, but they had also seen equipment limitations that seemed to prove their traditional approaches superior. Richardson's final report to the British Steel Association would conclude that American methods represented interesting experimentation unsuitable for serious industrial application. The speed was impressive, he admitted, but the equipment reliability problems would prevent any practical scaling of the process. What none of them could foresee was that Alexander Hawley had already begun designing solutions that would make their Sheffield methods obsolete within a decade, proving that American innovation succeeded not by avoiding engineering problems, but by solving them faster than anyone thought possible. Winter descended on Troy with the kind of bitter cold that made molten steel work both more dangerous and more urgent. Alexander Hawley spent December 1865 in his workshop, surrounded by technical drawings that represented the most counterintuitive engineering solution of the industrial age. While European steelmakers focused on building converter bottoms that would last indefinitely, Hawley was designing bottoms that would fail quickly and be replaced even faster. The mathematical reality was unforgiving. Each Bessemer heat subjected the converter bottom to 1600 degrees Celsius for 20 minutes, combined with violent chemical reactions that ate through even the best refractory materials. Traditional repair methods required complete cooling of the entire converter, a 24-hour process that included cooling time, manual reconstruction of the brick lining, and gradual reheating to operational temperature. During those 24 hours, competing Sheffield plants could complete 8 full production cycles using their slower but more reliable crucible methods. Hawley's breakthrough came not from metallurgy but from mechanical engineering. Instead of treating the converter as a permanent structure, he redesigned it as a modular system. The converter bottom became a separate component bolted to the main shell with a precisely machined flange system that could be removed and replaced without cooling the upper portions of the furnace. The concept required manufacturing tolerances measured in fractions of inches, gasket systems that could seal against molten metal, and lifting equipment capable of handling multi-ton components while they were still radiating dangerous heat. Patrick Murphy, the Irish furnace supervisor who had survived more industrial accidents than most men could imagine, initially regarded Hawley's plans with deep skepticism. Murphy had spent 15 years working around blast furnaces where equipment failure meant death, and his survival instincts rebelled against any system that deliberately planned for breakdown. But as Hawley explained the engineering details, Murphy began to understand that the American approach represented a fundamentally different philosophy of industrial risk management. "Mr. Hawley," Murphy said, studying the technical drawings spread across the workshop table, "you're asking my men to work on equipment that's designed to fail. That goes against everything we know about furnace safety." Hawley looked up from his calculations, recognizing the deeper concern behind Murphy's objection. "Patrick, what kills men in steel work? Unexpected equipment failure or controlled planned maintenance?" The question forced Murphy to confront his own experience. Most furnace accidents occurred when supposedly permanent equipment failed without warning, trapping workers near molten metal or collapsing structures. Planned maintenance, conducted when systems were properly shut down and cooled, was dangerous but manageable. Controlled failure, Murphy admitted reluctantly, but only if the control actually works. The first prototype Hawley bottom was installed in February 1866, during a blizzard that made outdoor work nearly impossible. The removable bottom section weighed 3,000 pounds and required a steam-powered crane system that Hawley had designed specifically for the replacement operation. The initial installation took 6 hours, far longer than Hawley's target time, but it proved the concept was mechanically feasible. The real test came after the 4th heat, when the converter bottom showed the expected signs of severe wear. Murphy's crew had practiced the replacement procedure repeatedly on cold equipment, but working with components that had recently contained molten steel presented challenges no practice session could replicate. The radiant heat made direct contact impossible without protective equipment, and the precision required for bolt alignment tested the limits of what steelworkers could accomplish under industrial conditions. Murphy himself operated the steam crane, positioning the replacement bottom with mechanical precision that seemed impossible given the harsh working conditions. His crew worked in coordinated teams, each man responsible for specific bolt patterns and gasket placements. The entire operation required communication through hand signals, as the noise from adjacent operations made verbal coordination impossible. 47 minutes after beginning the replacement, the new bottom was installed and sealed. The converter was ready for the next heat, without any cooling period for the main structure. The uptime improvement was dramatic and immediate, from 40% availability to 85% in a single modification. European observers who witnessed the replacement process struggled to understand its implications. Visiting German metallurgist Klaus Weber documented the procedure with scientific precision, but his reports consistently emphasized what he viewed as the wasteful nature of the American approach. They discard refractory materials that could be repaired, Weber wrote to his colleagues in Berlin. The American obsession with speed leads them to treat valuable furnace components as disposable items. What Weber failed to calculate was the economic impact of continuous operation. While European plants operated their crucible furnaces at 40% capacity due to maintenance requirements, Holley's modified Bessemer converters ran at 85% capacity. Daily steel production increased from 15 tons to 75 tons per converter, while labor costs per ton decreased proportionally. The productivity improvements attracted attention from railroad investors who had previously regarded American steel as inferior to imported British products. The Pennsylvania Railroad sent senior executives to observe Holley's operations in March 1866, conducting side-by-side comparisons between American Bessemer steel and the crucible steel they had been purchasing from Sheffield suppliers. Railroad testing protocols were brutally practical. Steel rails had to withstand repeated impacts from locomotives weighing hundreds of tons, temperature variations from sub-zero winters to blazing summers, and chemical exposure from coal smoke and industrial pollution. The Pennsylvania Railroad's metallurgical engineers subjected Holley's steel to stress tests that exceeded normal operating conditions by significant margins. The results vindicated Holley's engineering approach completely. American Bessemer steel showed superior grain structure compared to crucible steel, with more uniform carbon distribution and fewer internal stress concentrations. The 20-minute conversion time, rather than compromising quality, appeared to create more consistent metallurgical properties than the slower Sheffield methods. More importantly for railroad economics, Holley's production costs had dropped below $30 per ton, compared to $60 per ton for imported crucible steel. The cost advantage was so significant that railroad companies could afford to replace their entire iron rail networks with steel, a transformation that would reshape American transportation infrastructure within a decade. Murphy's initial skepticism transformed into evangelical enthusiasm as he watched his crew master the replacement procedures. "Mr. Holley," he told the engineer after a particularly smooth bottom change in April, "you've made steel work for the working man. No more waiting. A day for the furnace to speak again." The success at Troy attracted investment interest from across the American industrial establishment. By summer 1866, Holley was negotiating contracts for Bessemer plants in Pennsylvania, Ohio, and Illinois. Each installation would incorporate his modular bottom design, along with additional improvements he had developed through operational experience. European steelmakers continued to regard the American approach as temporarily successful but ultimately unsustainable. Their reports emphasized the material waste involved in regularly replacing converter bottoms without acknowledging the productivity gains that more than compensated for higher consumable costs. This fundamental misunderstanding of American industrial economics would allow United States steel production to surpass British output within 2 decades, transforming global industrial leadership in ways that European engineering tradition was psychologically unprepared to comprehend. Andrew Carnegie arrived at Alexander Holley's Troy plant on a sweltering July morning in 1872, carrying investment capital that would either transform American industry or bankrupt the most ambitious entrepreneur of his generation. The Scottish immigrant had already made his first fortune in railroads and telegraph companies, but at 37, he possessed the restless energy of a man who understood that industrial leadership belonged to whoever could scale proven innovations fastest and largest. Carnegie had studied production reports from Holley's operations with the methodical attention of someone whose survival depended on correctly predicting technological transitions. The numbers that captured Carnegie's attention were transformative in their implications. Holley's modified Bessemer process was producing 75 tons of steel per day from a single converter compared to the 3 tons per day that Sheffield's best crucible operations could achieve. More significantly, the American steel was testing at quality levels that matched or exceeded European standards, while production costs had dropped to $28 per ton. Carnegie recognized that these economics could reshape entire industries if applied at sufficient scale. "Mr. Hawley," Carnegie said, examining the latest converter bottom replacement with characteristic directness, "I want to build the largest Bessemer plant in the world. Not just larger than what exists in America, larger than anything in Europe. Can your systems handle that kind of scaling?" Hawley had been expecting this conversation since the Pennsylvania Railroad's successful adoption of his steel for their mainline replacements. Scaling from single converters to industrial complexes presented engineering challenges that went far beyond simply building more furnaces. The logistics of handling hundreds of tons of molten iron daily, the precision timing required for continuous operations, and the material flow systems needed for such massive production volumes would test every assumption about industrial organization. "The individual converter technology is proven," Hawley replied carefully. "The question is whether we can coordinate multiple units into a single production system. We're talking about manufacturing precision applied to industrial violence on a scale nobody has attempted." Carnegie's vision for the Edgar Thomson Steel Works in Braddock, Pennsylvania, represented the most ambitious industrial project in American history. 4 massive Bessemer converters, each capable of handling 20-ton heats, would operate in coordinated cycles to produce over 300 tons of finished steel daily. The facility would require its own railroad connections, dedicated blast furnaces for iron production, and support systems that could handle material flows measured in thousands of tons per week. The engineering challenges multiplied exponentially with scale. Hawley's modular bottom replacement system, which worked effectively on single converters, required complete redesign for multiple unit operations. The steam-powered cranes needed to handle heavier loads with greater precision, while the replacement bottoms themselves had to be manufactured to tolerances that pushed the limits of 1870s machining capabilities. More complex was the timing coordination required for continuous operation. Carnegie demanded production schedules that eliminated downtime between heats, which meant that while one converter was producing steel, another was being charged with molten iron, a third was undergoing bottom replacement, and the fourth was being prepared for the next cycle. The orchestration required railroad-like precision applied to chemical processes that operated at temperatures hot enough to melt copper. Hawley spent 8 months designing the Edgar Thomson facility, creating technical drawings that covered every aspect of the integrated production system. The converter mounting systems incorporated his latest improvements, pivot mechanisms that could handle 20-ton loads while maintaining the precision alignment necessary for proper bottom sealing. The crane systems were redesigned with steam power sufficient to lift replacement bottoms while they were still radiating dangerous heat levels. Construction began in January 1875, during one of the harshest winters in Pennsylvania history. The scale of the project attracted attention from across the industrial world, with observers from Britain, Germany, and France documenting every aspect of the American approach to mass steel production. European engineers were particularly skeptical of Carnegie's timeline, which called for full production within 8 months of groundbreaking. The first converter was completed in August 1875, followed by extensive testing that pushed Hawley's systems to their operational limits. The initial heats revealed problems that could only emerge at industrial scale, vibration patterns that affected equipment alignment, heat radiation that interfered with nearby operations, and material handling bottlenecks that threatened the entire production schedule. Carnegie observed these early operations with the focused attention of a man whose entire financial future depended on technical success. He had invested over $1 million in the Edgar Thomson project, representing more capital than most American companies possessed in total. The facility had to work perfectly, not just occasionally. The breakthrough moment came on September 18, 1875, during the first coordinated operation of all 4 converters. Hawley's crew had practiced the timing sequences repeatedly, but the reality of managing 4 simultaneous chemical reactions, each requiring split-second precision, tested human coordination abilities beyond anything previously attempted in American industry. Thomas O'Brien, now serving as head blower for the entire complex, coordinated the operations through a system of visual signals that allowed him to monitor all four converters simultaneously. The flames from each unit provided real-time chemical information, while steam whistles communicated timing information across the enormous facility. The noise was so intense that verbal communication was impossible, forcing the entire operation to depend on predetermined hand signals and mechanical precision. At precisely 2:37 in the afternoon, the first coordinated cycle was completed successfully. 4 20-ton batches of high-quality steel had been produced in perfectly timed sequence, with total cycle time of 18 minutes per converter. The chemical analysis showed carbon content averaging 0.4% across all 4 heats, with uniformity that exceeded European crucible standards. Carnegie examined the finished steel with instruments he had purchased from the finest German manufacturers. The grain structure was flawless, the chemical composition precisely controlled, and the mechanical properties superior to anything being produced in Sheffield or Birmingham. More importantly for railroad applications, the steel showed the consistent quality that allowed it to be used in critical structural applications where failure would be catastrophic. The economic implications became clear within weeks. Edgar Thomson's daily production of 300 tons equaled the monthly output of most European steel districts. Carnegie could sell railroad-quality steel at $50 per ton while maintaining profit margins that allowed for continuous reinvestment in facility improvements. The cost advantage was so significant that American railroads could afford to replace their entire iron infrastructure with steel, creating demand that would sustain massive production expansion. European observers struggled to comprehend the implications of Carnegie's success. Friedrich Krupp, whose family had dominated German steel production for generations, sent representatives to study the Edgar Thomson operations in detail. Their reports emphasized the massive capital investment required, concluding that such methods could never be economically justified in European markets, where demand was more limited and labor costs different. What the European analysis missed was the feedback loop between increased steel production and expanded steel demand. As Carnegie's low-cost steel made railroad expansion economically feasible, the growing railroad network created demand for even more steel for bridges, locomotives, and urban construction projects. American industrial growth was becoming self-reinforcing in ways that European economic models had never anticipated. By December 1875, Carnegie was already planning expansion of the Edgar Thomson facility while negotiating contracts for additional Bessemer plants across the American Midwest. Hawley's engineering innovations had proven scalable to industrial complexes that dwarfed anything in Europe, while Carnegie's business model demonstrated that American markets could absorb steel production volumes that would have glutted European markets completely. The transformation was accelerating beyond anyone's predictions, proving that American industrial success came not from avoiding European competition, but from creating entirely new scales of production that made traditional competition irrelevant. Success bred ambition across American steel centers with the dangerous momentum of an industrial avalanche. By 1878, Carnegie's Edgar Thomson Works had inspired a construction boom that stretched from Pittsburgh to Chicago, with each new facility attempting to surpass previous production records through converter sizes that pushed the limits of metallurgical engineering. The 20-ton converters that had seemed impossibly large just 3 years earlier were being replaced by 25-ton units, then 30-ton monsters that consumed raw materials at rates that strained entire regional supply chains. The mathematical progression was seductive in its apparent simplicity. If a 20-ton converter could produce 300 tons of steel daily, then a 30-ton unit should yield 450 tons with the same 20-minute cycle time. American steel entrepreneurs, intoxicated by production numbers that dwarfed European output, commissioned converter systems that treated metallurgy as a scaling exercise rather than a chemical process with inherent physical limitations. Thomas O'Brien, now recognized as the finest master blower in American steel, found himself managing converter operations that exceeded his intuitive understanding of flame behavior and chemical timing. The 30-ton heats at Carnegie's expanded facility generated flames that climbed over 40 feet into the air, creating thermal dynamics that couldn't be read using the visual cues he had mastered on smaller units. The sheer volume of molten metal undergoing simultaneous oxidation produced chemical reactions that happened too quickly for human observation to track effectively. "Mr. Carnegie," O'Brien warned during a particularly difficult week in March 1879, "these big converters are running ahead of our ability to control them. 20 minutes isn't enough time to judge what's happening inside 30 tons of reacting metal. We're guessing more than we're knowing." Carnegie, driven by competitive pressure from new steel facilities opening monthly across Pennsylvania and Ohio, struggled to balance O'Brien's technical concerns against production targets that investors expected him to meet. The economic logic of larger converters remained compelling. Fixed costs for labor, facilities, and support systems could be spread across larger production volumes, reducing the per-ton cost of finished steel to levels that made European competition impossible. But O'Brien's concerns proved prophetic as quality control problems emerged that hadn't existed with smaller operations. The 20-minute conversion time that worked perfectly for 20-ton heats left insufficient margin for chemical adjustments when dealing with 30-ton volumes. Phosphorus-rich iron ores, which could be managed in smaller batches through careful timing and temperature control, created metallurgical problems that couldn't be corrected within the rigid time constraints of the Bessemer process. The chemistry was unforgiving. Phosphorus removal required precise temperature management and extended reaction time that the rapid Bessemer cycle couldn't accommodate. As American steel plants exhausted the highest-grade Lake Superior iron ore and began using lower-quality sources with higher phosphorus content, the speed that had made the Bessemer process revolutionary became its fundamental limitation. Quality complaints began reaching Carnegie's sales office by summer 1879. The Brooklyn Bridge project, which had initially contracted for American Bessemer steel, rejected entire shipments after metallurgical analysis revealed inconsistent carbon distribution and phosphorus concentrations that exceeded engineering specifications. Railroad companies, previously enthusiastic customers for American steel, started specifying crucible steel for critical applications where failure could cause catastrophic accidents. European competitors, meanwhile, had developed the open hearth furnace process that addressed exactly the problems plaguing American Bessemer operations. Open hearth furnaces operated at lower temperatures for 2 to 4 hours per heat, allowing precise chemical control and phosphorus removal that Bessemer's rapid oxidation couldn't achieve. German steelmaker Friedrich Siemens documented his open hearth results with scientific precision that emphasized the superior metallurgical control possible, with slower, more methodical processes. The irony was profound and troubling for American steel leadership. The speed that had given American producers their competitive advantage was becoming the source of quality problems that threatened their market position. European steelmakers, initially dismissed as hidebound traditionalists, were producing superior steel using methods that Americans had rejected as obsolete. Carnegie commissioned extensive metallurgical studies to understand the quality problems affecting his largest converters. The research revealed fundamental chemical principles that hadn't been apparent during the successful scaling from small to medium-sized operations. Phosphorus removal required reaction time that scaled exponentially with batch size, not linearly. A 20-ton heat might achieve adequate phosphorus reduction in 18 minutes, but a 30-ton heat required 28 to 32 minutes for equivalent chemical results. The discovery forced American steel engineers to confront an uncomfortable reality. The Bessemer process had physical limitations that couldn't be overcome through mechanical engineering improvements or operational refinements. The 20-minute cycle time was dictated by the chemistry of iron oxidation, and attempting to process larger volumes within that constraint inevitably compromised metallurgical quality. O'Brien proposed a solution that seemed to betray everything American steel had achieved. "We need to slow down," he told Carnegie during a heated meeting in October 1879. "Not because we're afraid of speed, but because 30-ton heats need 25 or 28 minutes to produce quality steel. We've been trying to force chemistry to work faster than physics allows." The suggestion horrified Carnegie and his investors, who had built their business model on production speeds that European competitors couldn't match. Extending cycle times would reduce daily output and increase per-ton costs, potentially eliminating the economic advantages that made American steel competitive in global markets. Meanwhile, reports from European steel centers described open hearth operations that consistently produced higher quality steel than American Bessemer plants while maintaining reasonable production costs. The German steel industry, written off as backward just 5 years earlier, was gaining market share in applications where metallurgical precision mattered more than production speed. American steel found itself trapped by its own success. The rapid scaling that had created industrial leadership was generating quality problems that threatened long-term competitiveness. The engineering innovations that had solved mechanical problems, modular converter bottoms, precision timing systems, coordinated multi-unit operations, couldn't overcome the fundamental chemistry that governed steel quality. The crisis deepened through 1880 as major construction. Projects increasingly specified European steel for critical applications. The transcontinental railroad expansion that had driven American steel demand was slowing, while urban construction projects in New York and Chicago were demanding metallurgical quality that American Bessemer operations struggled to provide consistently. European technical observers, who had initially visited American steel plants to understand production methods they couldn't match, now came to study quality control problems they had avoided through more conservative scaling approaches. Their reports emphasized that American steel, while impressive in volume, suffered from the predictable consequences of prioritizing speed over chemical precision. The speed that had made American steel revolutionary was becoming the limitation that European competitors could exploit, proving that industrial leadership required not just the courage to innovate rapidly, but the wisdom to recognize when innovation had reached its physical limits. The question facing American steel was whether engineering ingenuity could solve problems that seemed to violate the fundamental chemistry of metallurgy itself. The solution emerged from Alexander Hawley's workshop during the brutal winter of 1885, not as a single breakthrough, but as a systematic reimagining of how speed and precision could coexist in industrial processes. Hawley, now 53 and bearing the physical toll of 2 decades spent in furnace heat and chemical fumes, had recognized that the Bessemer process didn't need to be abandoned. It needed to be liberated from the assumption that each converter operated independently. The twin converter system that Hawley designed for Carnegie's newest facility represented the most sophisticated coordination of industrial timing ever attempted in American manufacturing. Rather than trying to force 30-ton converters to complete perfect chemical reactions in 20 minutes, Hawley created a production cycle where 20-minute Bessemer heats were surrounded by complementary operations that provided the time necessary for quality control without sacrificing overall production speed. The engineering was mathematically elegant and operationally complex. While Converter A ran its 20-minute heat, Converter B was being charged with molten iron that had been chemically analyzed and adjusted during the previous cycle. Converter C was undergoing Hawley bottom replacement using pre-fitted components that had been prepared during earlier operations. Converter D was being prepared for its next heat with materials that had been tested and approved while other units were producing steel. Carnegie initially resisted the system's complexity, viewing it as an expensive solution to problems that seemed solvable through simpler operational improvements. The twin converter approach required precise coordination between multiple crews, sophisticated timing systems, and redundant equipment that increased capital costs significantly compared to single-unit operations. Mr. Hawley, Carnegie argued during heated discussions in February 1886, we're talking about doubling our equipment costs to solve quality problems that might be addressed through better worker training or improved materials handling. Hawley understood Carnegie's financial concerns, but he had calculated the economics of quality failure with the methodical precision of an engineer whose reputation depended on practical results rather than theoretical elegance. Andrew, we're losing more money on rejected steel and customer complaints than we would spend on proper equipment coordination. The Brooklyn Bridge rejection alone cost us more than this entire system upgrade. The first twin converter installation was completed at Carnegie's Homestead Works in June 1886, incorporating Hawley's latest improvements to the modular bottom replacement system along with steam-powered coordination mechanisms that allowed precise timing control across multiple units. The complexity was staggering: 4 converters, 8 steam cranes, 12 replacement bottoms in various stages of preparation, and coordination systems that required railroad-like precision applied to chemical processes operating at lethal temperatures. Thomas O'Brien, now serving as master coordinator for the entire system, found himself managing industrial operations that demanded skills no single person had ever needed to develop. He had to read flame patterns from 4 simultaneous chemical reactions, coordinate replacement operations on equipment radiating dangerous heat, and maintain production timing that left no margin for error or hesitation. The breakthrough demonstration came on September 22, 1886, during a coordinated production run that Carnegie had arranged to showcase American capabilities for visiting railroad executives from across the country. The timing was deliberate. Carnegie needed to prove that American steel could match European quality standards while maintaining the production speeds that made domestic manufacturing economically competitive. O'Brien began the demonstration at precisely 10:15 in the morning, initiating a production cycle that would continue uninterrupted for 8 hours. The orchestration required split-second timing as each converter moved through its 20-minute heat, while support operations proceeded in carefully choreographed sequence. Chemical analysis happened between heats rather than during production, allowing laboratory quality testing without interrupting the conversion process. The results vindicated every aspect of Hawley's engineering philosophy. Steel quality measurements showed carbon content uniformity of 0.4%, with variations of less than 0.05% across all heats. Phosphorus content, which had plagued earlier large-scale operations, measured consistently below 0.04%, well within specifications for critical structural applications. More impressive was the production rate. The twin converter system produced 420 tons of laboratory-quality steel during the 8-hour demonstration, equivalent to a month's production from the finest European crucible operations. The per-ton cost, including the expense of sophisticated coordination systems, measured $22, lower than Carnegie had achieved with simpler equipment that produced inferior steel. Railroad executives examined the finished steel with testing equipment they had brought from their own facilities, conducting stress analyses that exceeded normal operational requirements by significant margins. The American steel showed superior grain structure compared to European imports, with mechanical properties that qualified it for the most demanding structural applications. European observers who witnessed the Homestead demonstration struggled to reconcile the apparent contradiction between speed and quality that American engineering had achieved. Friedrich Krupp's representative, Heinrich Müller, documented the twin converter operations with scientific precision while admitting that German steelmaking had no equivalent to the systematic coordination he was observing. The Americans have solved the fundamental problem of industrial chemistry, Müller reported to his superiors in Essen. They have created time for precision without sacrificing speed of production. Our open hearth methods, while producing excellent steel, cannot match their combination of quality and volume. The vindication was complete and decisive. By 1890, American Bessemer plants using Hawley's twin converter systems consistently outproduced European facilities while maintaining quality standards that exceeded international specifications. Carnegie Steel alone produced 322,000 tons in 1890, more than the entire German steel industry, and at quality levels that made European competition economically impossible in American markets. The impact extended far beyond steel production statistics. American structural engineering, freed from concerns about material reliability, designed bridges and buildings that pushed the limits of what iron frame construction could achieve. The transcontinental railroad expansion accelerated as high-quality steel rails became available at costs that made previously uneconomical routes financially viable. European steelmakers, faced with American competition that combined superior quality with lower costs, began adopting coordination systems based on Hawley's innovations. The open hearth furnaces that had briefly threatened American dominance were integrated into timing cycles that borrowed heavily from Bessemer operational principles. Alexander Hawley died in Brooklyn on January 29, 1882, 4 years before his twin converter system achieved its full vindication. But his engineering philosophy had transformed American industry permanently, proving that the most complex problems could be solved through systematic analysis rather than cautious tradition. The Bessemer converter, perfected by American engineering, remained the fastest steelmaking process ever invented. When electric arc furnaces finally replaced Bessemer operations in the 1960s, it was not because American methods had failed, but because environmental regulations and scrap recycling made different processes more practical. The 20-minute conversion time that European experts had declared impossible in 1865 remained unmatched by any steelmaking technology developed in the subsequent century.